it remains stored up in the peat. And that's why you can use peat as a fuel, rather like you can use coal. In this part of the peat works, extraction of peat is actively going on, and it's for horticultural use, not in fact for burning.
Yeah.
They're much lower down in the peat, it's much older, and you can see different plants. Over here, there's a very big birch tree stump. You can see the stump of the birch here, and the roots going along there, and just below it you can see the clay. And if we dig into this clay, we can see the remains of plants, roots of plants, that were the first ones growing on this bed of clay down into it.
But the clay itself is marine clay.
Yes, it has fossils in it, which are the ones that the animals that live in the sea.
Yeah. So we're seeing the change from marine to
Indeed, that's right.
terrestrial.
And below this marine clay, there's another layer of peat. But to get into it, we shall need a peat borer right through into the peat underneath.
Right.
I've got this sampler down through the clay into the peat here, and it's very hard. Give us a hand up. Good. I will stop and put it in the air to take some of these rods off. Okay, now if you hold on to this bit here, I'll take the top two off. Now there are two rods there. That means we've gone down 3 meters. And we still have lots more to go. It's 4.5. That's 6. And the bottom of the sampler is about 6.5 meters into the clay. Clear all this clay off the top, and underneath there you can see the peat. So if we peel a piece of this peat off, there we are, you'll see that it's quite different. It's got lots of wood in it, but at the same time it's not got any leaves or plants or things like that in it. If we look at a piece of peat here, which is from above the clay, you can see all that growth structure, leaves, stems and things are missing. This then has been subject to pressure by the clay. It's been partly compressed, partly dried out, and in fact it looks a bit like brown coal.
This is brown coal from Devon. You can actually see the woody grain of it. It's actually fossil timber from the Californian redwood, the tree that still grows in California now. Well, the peat was a few thousand years old. This brown coal is 30 million years old, and of course the coal we burn is 300 million years old. But we've still got the fossils of the plants that formed that. They come in 3 groups, really. First of all, there are the leaves of plants that were in the coal forests. Here you can see a very good example of a fern-like leaf. There's another there, and somebody found this super pebble from the shales that lie just under the coal seams. It's what was the soil under the forest in which these plants grew. The second lot of samples are the fruits of trees that grew in that forest. This is a cone, like the cones we now have on pine trees. And then finally there are the group that are pieces of the plant. This is the flattened stem of a horsetail, and here is a cast of the same kind of stem. You can see the characteristic cross lines of the horsetail stem with its grooving along it. We still have horsetails, of course, in wet places and on abandoned railway cuttings and so on. In fact, all these species are extinct, but on the Earth's surface there are the forests still of very similar structure to the coal forests. They're nearly all tropical and on the edges of the tropics, in, for instance, the Everglades in Florida. Most of these trees have their roots in water. When they die, they fall into water and decay away from the air, forming a peat that may one day become coal. One of the things about getting hooked on geology in the landscape is that you can't afford to miss any holes in the ground. And inevitably near any town there are bypass construction sites now. This one exposes coal seams. That you can see it over there. They're little ones, they won't solve the energy crisis, but nevertheless they are exposed on both sides. You can see a coal seam over there that runs behind this new concrete structure and round and to me over here. From the rocks that are here now, you can actually work out the setup that existed 300 million years ago when the coal was being first developed. If you ignore these long smears which the JCB has made, then you can see a sequence of rocks starting with clays and shales and muds down here, then sands. There's a strong sandstone band there with much coarser grains brought down by a river to this delta, then more clay and shale, until the build-up in this shallow sea is sufficient to get it above sea level and vegetation can move in. Even forests then develop, soil below them is still here, and if we look very closely at the soil, then we can find within it, by poking about, the fossils of the roots of the forest. And so from the soil with its rootlets, the seat earth, the miners would call it, the seam itself sits, it's about 2 feet, 2'6" thick, represents about 60 feet of peat, which would represent the whole volume of the forest that grew on this particular shoal top. Then the whole thing begins to sink again, and it actually slopes this way, so if I walk along I can come out above it. And above the seam, starting around here, there, we go through the sequence again of shales and muds and some little sandstones. And the sea moved over, deposited everything. We've even found fossils in here, the little mussels. You can see the 2 valves there of a mussel shell. And so the build-up begins again, and more vegetation will move in, and another coal seam will be beginning. And of course, the North Derbyshire coalfield is only one of the coalfields spread through the British Isles, all of which represent similar sequences. The position of these coalfields today reflects the lie of the land during the Carboniferous. The forests that made the coal were, like the Everglades, on the coast, mostly in swamps around the coast of an island called by geologists St. George's Land. The other fossil fuel that we burn to release the energy stored by other organisms millions of years ago is, of course, oil. Oil is not formed by the big plants and trees that form coal, but it's formed by those little tiny microscopic animals and plants that swim around in the sea that we call plankton. They eventually die and fall down to the bottom of the sea and accumulate in the mud. Now there, the mud is compressed into a rock and they are warmed slightly, maybe only to 65 degrees centigrade, but that is sufficient, as far as we can tell, to release petroleum. Now, we're not quite sure of the exact conditions that are necessary for this process, but we are clear that there are a number of criteria that have to be fulfilled before we can find oil in sufficient quantities to make it worth using. The first thing we must have is that rich organic mud at the bottom, which we call the source rock. And once the petroleum is released, as this is warmed gently, so it rises, and we must have, therefore, something for it to rise into, a rock which must be porous, it must have holes in it, and the holes must be joined together, it must be permeable. So we need that on top of the source rock itself. But we don't want it to migrate upwards too far, so we need something to seal it. We need an impermeable rock that we put on top of that, which we call the cap rock. And however many other layers of rock are put on top of that, we still need, right at the bottom, that sandwich of the source rock, the reservoir rock, and the impermeable cap rock. And then the final thing we need is something to make sure that the oil remains concentrated, that it doesn't migrate sideways in the reservoir rock itself. Now, there are many ways of forming traps for it, but one of the commonest is, in fact, for an earth movement to have buckled the strata like that to make an anticline. Now, anticlines are very common geologically, and they're often disguised at the surface by being eroded. And obviously the process of erosion can in some cases, break into the reservoir rock, and then the oil seeps out at the surface. We have a kind of natural pollution, and we lose our possible source. So there are 5 golden rules that must be obeyed if an oil prospector is to strike rich. First, you need a source rock, rich in organic matter, and second, you need heat to release the crude oil. Third, a reservoir rock, permeable, so the light oil rises through it. Fourth, a cap rock, which is impermeable and keeps the oil in the reservoir. And fifth, an arrangement of strata that traps the oil. One such trap is in an anticline, but there are countless other types around the world. Another quite common trap is made by movement along a fault. I went to do my own bit of prospecting in Dorset with Dick Selly, a petroleum geologist from Imperial College in London.
Well, I bring my students along here every Easter, and most of these people have been in the oil industry already for a year or two.
I see.
And during the week, I bet them a bottle of wine for the first student to find any oil in the place. And of course, I bring them along here and I don't say anything, and then suddenly they come up, and it's very interesting to see who spots it in this part of the world. You can see on the sea water there the iridescence as some oil is coming up to the surface. This is an oil seep. And what we have here is a porous sand bed saturated with oil just below the sea floor. The oil is coming up through the gravel on the beach up onto the surface of the water, and every now and again you can see these little drops, this iridescence, coming up to the surface. So this is evidence that once there was here an oil field of some size. Some of the 5 criteria that we can recognize here are that we have underneath us a reservoir rock which has porosity and permeability. Beneath that there must have been a source bed, a shale of some sort to generate that oil. And above the reservoir a seal, a cap rock, which is impermeable, preventing the escape of the oil. In Weymouth Bay out here we've got evidence, we can map that there was once a very large anticline which was the trap in which the oil was contained. Yeah. But the problem is that Mother Nature has eroded the crest of that anticline out from the core of Weymouth Bay, so what we're seeing here is just the leftovers, what's left behind. Most of the oil has dissipated at the surface. Yeah. Well, here we are. We've now walked about 200 meters along the beach, and there it is.
That's super.
That's it. That reservoir sand that we saw down on the beach with the oil seeping up through the beach gravel is now here, cropping out in the cliff. The base of the reservoir is about where your boots are, and the top of the reservoir is about here. It's very thin. It's only about 3 or 4 meters, tiny by North Sea standards or Middle East standards. Yeah. But that is an oil reservoir that was, and here is the oil actually seeping out. You can see the way it's smeared down the cliff here, running out of the rock. That's the sand, a little bit of student erosion, unfortunately. But let's see if we've got a piece of this handy. Yeah. There we are. That's it. Smell that. That is crude oil.
Oh yeah, that's incredible, isn't it? The south coast of Britain.
Yeah.
I like it.
Now, shall we see if we can actually get it to ignite? Have you got anything with you for that?
We can try.
All right.
It's a bit windy.
Well, there you are. We've got some smoke going. You don't seem to have been able to get it actually to light, but that's pretty good. There's some smoke and a tremendous smell of burning oil coming off.
Well, now, you know, I've seen this oil in 2 places, but the structure still isn't clear. Can you sort it out for me?
Okay, well, perhaps if I could draw a cross-section through where we're standing now, I can show it to you. If you could hand me the pad there. Thank you. This is south, north, and I'll try and draw a cross-section through the area. This is Portland Island to the south of us, and here is Weymouth Bay. And we're now standing right on this little cliff, the coast here. And the topography as we come inland is doing something like this. Now the strata are deformed, they're folded into this large Weymouth anticline that we've been looking at here. There is a downfold, a syncline that one can see here, and another anticline developed to the north, and we'll be able to see this later on, how the strata are deformed in that way. So this bed, this sandstone bed that we've been looking at, is on the north side of this Weymouth anticline, and it continues in the subsurface down here and is deformed into another anticline to the north of us like this. Now, in terms of where the oil is, we have just been looking at an oil seep here on the beach in this reservoir sand. And this has told us that once upon a time in Weymouth Bay, above Weymouth Bay, there was an oil field of some dimensions. So the theory behind exploration here would be to say, right, this anticline contained oil, oil was generated, we have a reservoir bed, a seal, a cap rock above it, and a source below. Let's try and find the next structure, the next anticline. So the exploration philosophy was to go to the north here to this anticline, where the same bed is occurring but in the subsurface, and to say, could we drill on the crest of that structure, and could there be an oil field in this position here? Well, this is it. Here we are now, walking up the southern flank of the next anticline to the north of us. Yeah. Behind is Weymouth Bay with the coast where we saw the oil seep, the eroded crest of the Weymouth anticline and Portland. Yeah. Now we're walking up this southerly dipping slope of the next anticline. And this is it, here. We're now looking right down the axis of this next anticline to the north, and you can see there the southerly dipping strata, that little quarry, that little limestone quarry there. You can see the beds perhaps dipping to the south. There's the crest of the anticline, the breached core of it, and the strata dipping over to the north on the other side. Lovely example of what in the Midwest of the States is called a sheep herder anticline. It is so obvious that even the shepherds can see them and tell wandering oil prospectors about them.
That's nice.
Now, if we look on the geologic map, you can see where we've come from. This is the beach where we saw the oil seep down there. We've moved northwards to this point on the map, and there are a whole series of these little anticlines along this east-west trend. Yeah, I see. And about 30 years ago, several wells were drilled to test these structures here.
Oh, I see. And did they produce anything?
Unfortunately, no.
Oh, that's sad.
Well, the geology is a little more complex than I've told you about just now. There are at least 3 phases of folding here, and it is possible that the oil migrated through this part before the traps were actually formed. This is one possibility.
Yeah. But in fact, oil is produced in Dorset, isn't it?
Yes, indeed. There is a small oil field east of here at Kimmeridge Bay. This is a pumping oil well, often called a nodding donkey. The oil is fairly shallow and no pressure in it at all. It's not going to come out like a great big gusher, like a soda water siphon. What's very nice about this location is that the well is situated on the crest of an anticline. And over on the left, the strata are dipping very gently out to sea in the cliff there. Rising up in the cliff, you can see where they're horizontal, and the oil well is located right on the crest where the strata are horizontal, and then dipping off to the right again very gently, the north limb of the anticline.
So we're seeing a whole anticline in this cliff. You know, it's textbook stuff, isn't it?
That's right. Very nice. And the well right where it should be on the crest of it. Now, the first well that was put down here only went down as far as the strata with the oil seep that we saw earlier. But that was actually sub-commercial. I see. And about 20 years later, they drilled much deeper and established commercial production in a deeper reservoir, which has its own separate cap rock above it.
So this stone on the beach, all these rocks on the beach have come out of the cliffs we've been looking at?
Yes, that's right. This is, in fact, some of the Kimmeridge shale, which is very interesting of its own right. It's very rich in organic matter, and there are layers in this of oil shale. And for many years, the oil shale was used as a source of oil being distilled from it, where this isn't happening at the moment. And in fact, in some places, there is so much organic matter in the shale that the cliffs along here catch fire spontaneously and burn for years.
In fact, the burning cliffs at Weymouth became something of a local tourist attraction. Our great-great-grandparents arrived in boats and carriages to warm their hands at the flames of a noted geological phenomenon. This print was published in 1827, but the rocks around here still ignite from time to time. Only a year ago, the holidaymakers in this bay shared the sun and sand with the smell of burning oil.
But the other really interesting thing about this shale at Kimmeridge Bay is that we can trace this formation northeastwards across the British Isles, and it is still present in the North Sea, several thousand feet thick in the subsurface. And it's still very rich in organic matter there. And most petroleum geologists believe that that is the major source rock for North Sea oil.
Oh, I see. So this mucky stuff in Dorset is a hint of Britain's economic saving.
If you put it like that, yes.